All right, guys, we are here for, where am I, 16.3 and 16.4. There are no problems for these sections. It is all conceptual. Okay, so conductors in equilibrium. Let me zoom out just a little tiny bit. Okay, so if you notice, we have a conductor here. A couple things. First of all, it is charged. It is positively charged. If you notice, it has an irregular shape, okay? And so if you're looking here, okay, the charge is concentrated. Okay, that's not the greatest. Okay, sorry, trying out some new technology. If you notice here, the field inside of the conductor here is 0. Let me just do that. So the field inside of this conductor is 0. But if you notice, extending from the surface of the conductor, the field is going outward because it's positive. Okay, if you notice, these field lines we drew here are all perpendicular to the surface, and there are more of them in the area where there is more charge stored. Okay, the potential is everywhere constant on the surface of the conductor. Okay, so the ability to do work caused by its electric charge is the same everywhere on the surface. Okay, and what you're going to end up finding out is if we connect these dots or these lines and we connect them perpendicular to each one, sort of like connect the dots, we'll have these sort of like a topographic map of potentials. Okay. The potential inside of the conductor is always equal to whatever the surface value is. So although there is no field, there is potential inside. Okay. Going on to the next one. There's a unique unit here. We call it the electron volt. It's just like an equivalent unit to compare things. So it's defined as the kinetic energy that an electron gains when it's accelerated through 1 volt of potential. Okay. So usually electrons in normal atoms, not excited ones, usually it's in the 0 to 10 range. Okay. Excited electrons go to the thousands range. Okay. And high energy gamma rays have millions of electron volts. So it's just a comparative way to show charges and potentials. Okay. All right. So then we have these equipotential surfaces. So an equipotential surface is where every place on that line or on that surface has the same electric potential. Okay. And like I said, if you draw field lines, if you connect the field lines so that the lines are perpendicular to each other, those lines connect sort of like a topographic map, places of equal potential. So here is an example with a point. So my test charge here is positive. The orange lines are the electric field going out proportional to the charge of the object. Okay. And then if you notice, they connected these dots, and every dashed line here is perpendicular to the field line it crosses. Okay. So each one of these lines has a different potential, but everywhere on these green or these dotted circles has the same potential. So say this has 10 volts of potential, this has 7, this has 5, this has 1. Okay, I'm just making up numbers, but that way you can kind of visualize. Okay, it's a lot like a topographic map. Here's another example where I have 2-point charges. So again, the field lines are there, just like we drew, coming out of the positive, going into the negative. And then we connected all of the dots perpendicularly. So see how these field lines or these potential surfaces are kind of shaped weird because they have to cross every line tangent or perpendicular. Okay, so every one of these blue areas has, every point on those blue lines has the same electric potential. Okay, and that are both of those sections. So they're only about two pages in your book. Read through them. If you have any questions, let me know. There really aren't any textbook questions There might be some conceptual ones, but the next section is all about capacitors, which is pretty exciting. Have a good day, guys. Miss you.